Geometry of dynamic tetrahelix and field structures. Part 3a. The harmonic behavior of the dynamic tetrahelix will be explored. Part 3a. Harmonics of dynamic tetrahelix. Up until now, the tetrahelix we have explored have not allowed for overlapping elements. In this section, the simulator will allow for the elements to overlap. To examine the inner structure of these dynamic tetrahelix, the tetrahedral elements will be replaced with a simple arc shape. At certain twist angles, the arcs completely overlap and align to form harmonic patterns that also create closed loop circuits. As a concept, could these loops possibly be used to model field structures? Harmonics of loop tetrahelix. When twist angle scaling is applied to a loop tetrahelix, it reveals harmonic patterns as the elements align and overlap each other, along an ever-changing circular path. Each unique subsequence represents a family of harmonics of different magnitudes. The magnitude of the harmonic equals the total length of the tetrahelix, divided by the bit length of the subsequence. In the next video, subsequence 211-21212 will be used as an example to illustrate various harmonics with different magnitudes within the same family. The total length of the tetrahelix is set to 16 for this example. With a subsequence bit length equals 8, this represents the harmonic with a magnitude of 2, or the second harmonic. The total length of the tetrahelix will be increased by 8 elements at a time, to illustrate some harmonics with a higher magnitude. Harmonics of different magnitudes. In this example, there is a gap in the loop tetrahelix at the default twist angle of 120 degrees. The twist angle is then changed to 112.37 degrees to close the gap and reveal the second harmonic. The length is then increased by 8 elements and rebuilt. The twist angle is then changed to 133.02 degrees to reveal the third harmonic. The length is then increased by an additional 8 elements and rebuilt. The twist angle is then changed to 143.68 degrees to reveal the fourth harmonic. The length is then increased by an additional 8 elements and rebuilt. The twist angle is then changed to 150.38 degrees to reveal the fifth harmonic. The fifth harmonic has inherited all of the lower-level harmonics, which can be demonstrated by decreasing the twist angle to reveal the lower-level harmonics. Examples of the fifth harmonic. This video illustrates several different loop tetrahelix that have a unique subsequence that reveal its unique fifth harmonic. Refer to the yellow status bar for details for each harmonic. Each of these loop tetrahelix create a closed loop circuit for the displayed twist angle where the oldest and youngest elements align with each other. The loop tetrahelix is closed when the red and blue arcs completely overlap. You will notice that by using arcs for the elements, the internal structure of the loop tetrahelix can be seen more clearly. For each subsequence, I'm only showing one magnitude of the harmonic, however, there are many more harmonics that would show up at different twist angles and different lengths. This will be explored in more detail in subsequent videos. Harmonic boundary conditions. I have found that there are at least 2 different types of loop tetrahelix that have different boundary conditions for the twist angle extremes of 180 degrees and 0 degrees. In one case, at 180 degrees, the tetrahelix forms a linear wave, and at 0 degrees it forms a ring. In the other case, at 180 degrees, the tetrahelix is constrained to a circular disk, and at 0 degrees it forms a ring. The next video illustrates these 2 examples. Harmonic curvature, example 1. At a twist angle of 180 degrees, the tetrahelix forms a linear wave structure. As the twist angle decreases, its unique, ever-changing curvature is revealed, as well as the numerous harmonic patterns that exist for this subsequence. As the diameter of the loop tetrahelix decreases, the elements overlap and form multiple loops, as the tetrahelix wraps around itself several times. Note that there is only one axis of symmetry for the various harmonics that are revealed. At a twist angle of 0 degrees, this tetrahelix forms a ring. Harmonic curvature example 2. At a twist angle of 180 degrees, the tetrahelix is constrained to a circular disc. As the twist angle decreases, its unique, ever-changing curvature is revealed, as well as the numerous harmonic patterns that exist for this subsequence. As the diameter of the loop tetrahelix changes, the elements overlap and form multiple loops, as the tetrahelix wraps around itself several times. Note that there is only one axis of symmetry for the various harmonics that are revealed. At a twist angle of 0 degrees, this tetrahelix forms a ring. Twist angle scaling of spiral tetrahelix. Twist angle scaling can be applied to the spiral tetrahelix to form a closed loop. At a twist angle of approximately 83 degrees, this spiral tetrahelix creates a closed loop. This complex structure could only be revealed by using arcs as the elements of the tetrahelix. When the elements are replaced with tetrahedrons, you can see that the internal structure of the tetrahelix would be hidden. Examples of twist angle scaling of spiral tetrahelix. Twist angle scaling can be applied to spiral tetrahelix, and at one particular angle, complex loop structures are formed. Here are a few examples of spiral tetrahelix, defined with a unique subsequence. Using arcs as the elements of the tetrahelix help to reveal this complex internal structure. Refer to the yellow status bar for details for each spiral tetrahelix. Part 3A, Wrap Up. This concludes Part 3A of the presentation on the harmonics of dynamic tetrahelix. In Part 3B of the presentation, the fractional harmonics within dynamic tetrahelix will be explored.